Hello, and welcome to the full course session on CAE Simulation using SolidWorks, your gateway to mastering finite element analysis and performing advanced simulations for real-world engineering challenges. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can now proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on SolidWorks and other engineering tools. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the basics of FEA analysis. You'll learn the fundamentals of the stress-strain graph and be introduced to various types of FEA analysis, both linear and nonlinear simulations. We'll also walk you through the different processes involved in performing an analysis, helping you understand how FEA affects different models. In the second chapter, we'll focus on performing FEA analysis on a uniformly loaded cantilever beam. You'll learn how to design the model, conduct static analysis, and run 1D, 2D, and 3D analyses on the same beam. We'll show you how to perform a design study and compare the results, helping you develop a deeper understanding of structural analysis in SolidWorks. In the third chapter, we'll cover buckling analysis using a cyclonic separator stand. You'll learn how to import a neutral file, clean up the geometry, and carry out structural analysis. We'll introduce the concept of buckling analysis and show you how to enhance the factor of safety for the model in SolidWorks. In the fourth chapter, we'll delve into fatigue analysis with an S-hook. You'll explore how to utilize the SN curve for fatigue analysis, apply different loading types, and import results from static analysis to fatigue analysis. We'll also guide you through creating animations from the analysis results. In the fifth chapter, we'll focus on drop tests. You'll learn how to perform a drop test on a model like a PCB board and understand the factors that impact the test results. We'll show you how to post-process the simulation and interpret the outcomes. In the sixth chapter, we'll introduce you to frequency analysis, where you'll explore the concepts of vibration and modes of vibration. You'll learn how to use the available solvers in SolidWorks for frequency analysis and perform frequency analysis using a PCB model to understand the different mode shapes. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with CAE Simulation using SolidWorks.
Hey everyone. Welcome to a new video in finite element analysis using SolidWorks. So in this video, we'll be discussing the basics of FEA and briefly looking on the various analysis system present in a SolidWorks simulation module. So let's begin with the presentation. Finite element analysis is popularly abbreviated as FEA. So in this analysis method, we use finite element method to solve structural problems. Here, the whole model is discretized into small elements which consists of nodes on which the governing equations will be solved. Once the governing equations are assembled for the whole model, several matrix solving techniques are employed to solve for the unknowns. So once we know the values for displacement, so we derive the stress and strain contour plots for the whole model. So the popularly used FEA packages are SolidWorks, ANSYS, and COMSOL. Apart from these commercial packages, there are several open source FEA packages available like CodeAster and several others. You can even try them out to begin with. So now let's move on. So this is the stress strain plot for a material. For every model that we use in a finite element analysis, it is going to be made up of a material. So each material will have its own characteristics which is vital for a finite element analysis. To get this stress strain graph for a material, we perform tension tests on the material and plot the strain for the stress developed due to the loads applied. Let's discuss this graph in detail. So once we complete the experiments, we have the strain plotted in the x-axis and the stress plotted along the y-axis. Let's rename the origin as O. As the load is increased, we plot the corresponding strain along with the stress to get this stress strain graph. Once we get this stress strain graph, so we divide the curve into different regions depending upon how the material behaves. First, between the points O and A, the material tends to behave linearly. That is, the stress value is linearly proportional to the strain produced. Now, so within this region, if we unload the loads that we have applied on the material, the model regains back to its original shape without any deformation. Hence, this region is called limit of proportionality, and A is the elastic limit point. And within this region, the Hooke's law is valid. That is, stress is going to be linearly proportional to the strain produced. Once the material passes this elastic limit, it tends to move into a plastic region where there is small deformations even after unloading the loads on the material. Now, as the plastic deformation sets in the material, the maximum value of stress and the minimum value of stress produced during the plastic deformation denote the upper and lower yield stress point of the material. If we increase the load even further, we reach a point called the ultimate stress point, which gives the value of the maximum stress the material can withstand. As we pass this ultimate stress point, we end up in a rupture point, which denotes the breakage or the failure of the material. So this is how the stress strain graph is divided into several regions. Once we have plotted this graph, we derive other material properties like Young's modulus and Poisson ratio to define the materials. You will be provided a reference material and a challenge to work on to refresh your concepts on the basic terms involved in a FEA problem. So let's move on with the presentation now. Static analysis. As the name suggests, simulation is going to be independent of time. That is, the loads applied are not dependent upon time. dF by dt is going to be 0. Hence, we call it as a static analysis, and this static analysis is broadly classified into linear and non-linear analysis. So as the name suggests, there is a linear relation between the stress and strain in the linear analysis, while on the non-linear analysis, the relation is no longer linear. Secondly, in the linear analysis, the material obeys Hooke's law and the deformations are small. But on a non-linear analysis, the deformations are large and will not be proportional to the load applied. Finally, the material properties are assumed to be constant in a linear analysis, and hence this type of analysis can be applied only within the elastic limit. But in a nonlinear analysis, the material properties along with the nonlinear relation is included, so that after each iteration, the stiffness of the material is updated to capture the nonlinear effects in the simulation. Since it is going to update the stiffness value for the material after each iteration, it is computationally heavier than the linear analysis. Now in SolidWorks, if you perform a linear analysis on a model, you tend to assume that your stress values are between O and A. And in case if you tend to increase the loads beyond this limit, your solver tends to follow a path which is unreal. Your stress value tends to increase linearly, even though there is a realistic nonlinear path available. Further, if the solver detects large plastic deformations in the model and you are performing a linear analysis, it will prompt whether you want to switch the analysis into non-linear. And if you agree to that, the solver will convert the simulation into non-linear simulation and proceed. Else, it will take this path and give you the corresponding results. Let's move back to the presentation. Any FEA problem involves three major steps. The first one is pre-processing, the second is solving, and the final part is the post-processing. In the pre-processing step, we define the material properties for the model and then discretize the whole model into small elements. So this process is called meshing. After meshing the model, we define the loads and constraints for the solver to proceed with the solution. In the solution process, depending upon the type of analysis, the solver employs different algorithm to solve for the unknowns. And after the solution is done, the derived quantities like stress, strain are then calculated. In the post-processing, we'll be looking at the different stress and strain contours that is produced after solving the FEA problem. These plots will be used to generate the report on the analysis done. Let's first talk about meshing. So SolidWorks majorly uses two types of elements, that is the triangular and the quadrilateral elements. In a basic triangular elements, we have 3 nodes, and in a basic quadrilateral element, we have 4 nodes. Now any model that we will be using for a finite element analysis will consist of intricate shapes and profiles that are captured even after discretizing them. Hence, depending upon how complex your model is, your mesh needs to be refined. Further, after performing any simulation, to check the accuracy of the results, we perform grid dependency tests. That is, we run the same simulation by refining the mesh up to a point where the results do not change even after refining the mesh further. So this is called the grid dependency test. For any mesh refinement, we have 2 methods that SolidWorks provides us with. One is called the H refinement and the other is called the PE refinement. So in the H refinement, we refine the mesh by including more elements into the model. While in the P method, we keep the number of elements as the same, but we tend to increase the order of the elements that we are using in the model. Also, in H method, since we increase the number of elements, we tend to decrease the characteristic length of each element. In the P method, the characteristic length remains the same, while we increase the complexity of the shape functions that is included in the element. Look at an example on how H refined and a P refined mesh should look like. So here, in the figure number 1, we have the original mesh. We have this rectangular geometry which is discretized. So in the second, we have a H refinement. And in the third diagram, we have the P refinement. Originally, the mesh consists of 6 elements. When it's H refined, you can see the number of elements have been increased by a factor of 4. And this factors can be user defined. Hence, you can control the number of elements you want to include. Thus, you can see we have refined the mesh by increasing the number of elements using the H refinement mesh. Finally, in the P refinement, even though the number of elements remain the same, we have introduced mid-side nodes to increase the degree of the element being used. We end up using a higher order element to get accurate results. So thus, we use P refinement to increase the order of the element used in our mesh. Now let's proceed with the presentation. In FEA, depending upon our requirement, we tend to reduce the computational power required to solve a problem using different types of analysis. So depending upon our requirement, FEA analysis consists of 1D, 2D and 3D analysis. First, let's start with 1D. So if your FEA analysis consists of a model which has one of its dimensions significantly larger than the other, then we tend to go for a 1D analysis. So if the model that you are going to use in your FEA analysis has a dimension which is significantly larger than the other dimensions, then we tend to go for a 1D analysis to obtain the required results. For example, let's consider a long beam, and I am interested in looking at the deformations caused by bending. Since the beam is long enough, a 1D analysis is sufficient to produce the required results. 1D elements are basically used to represent long members like beam, and hence they help reduce the computational power required to solve the problem. Now 2D elements that are basically referred to as shell elements, and these shell elements are provided with a thickness to actually represent the model. So these are predominantly used when we have thin sheets and shell structures in our model, and further we can accurately derive bending stress on the part. Using this type of elements in the simulation helps in getting accurate results with a less computational effort than going for a 3D. Now finally the 3D. Once if you have obtained all the required results from 1D and 2D, but still you want to understand the stress produced on the whole model, you tend to go for a 3D analysis which is computationally heavier. We have solid to represent the models here. Finally, after the simulation is done, we look at the various stress and strain plots to infer our findings from the simulation. We'll be looking at how to perform a 1D, 2D and 3D simulation on a beam problem in the next video. So now let's move on. SolidWorks simulation module consists of various analysis systems specifically designed to solve different types of FEA problems. First one, we have the static problem. Here, as the name specifies, we assume the forces are independent of time, and it helps us to calculate the stress, strain, the displacement produced for applied load in the form of a point, surface or a thermal load. This is basically about the static module. Now in the fatigue, when you have a model which is going to be acted upon by a repeated load, and you want to study the failure of the material due to such kind of a load, we use this fatigue model. From the fatigue analysis, we'll be able to understand the behavior of our model under cyclic loads. In the frequency model, we'll be able to analyze a model which is subject to a force and the body vibrates at a certain frequency. As we all know, every body has its natural frequency, and this natural frequency can be found out by using this frequency module. From this type of analysis, we can look at different mode shapes associated with the model. So in the buckling model, apart from the failure due to the material strength, a lengthy member like a beam can fail due to axial instability. So such kind of analysis can be performed using the buckling module, and SolidWorks helps us visualize failure of a model subjected to axial loads by calculating the multiplication factor to predict the failure. Here SolidWorks plots the buckling load factor, which will help us predict the failure due to buckling. In the thermal module, we'll be able to study the temperature gradients and temperature fluxes in the body due to loads like conduction, convection and radiation. Next, in the optimization, every finite element analysis is performed to obtain the optimum design. So for us, the optimum design may be the one with the least mass or the least stress. So depending upon our requirement, we can ask the solver to iterate between different values of the dimensions and arrive at the optimum design parameters. This module will be very useful in performing optimizations. Now, next we have pressure vessel design. So SolidWorks has a special module which is customized for a pressure vessel design, and this module helps you perform typical analysis that is usually done while designing a pressure vessel. Now to the vibration part, here the loads are specified as power spectral density functions. Don't worry if you are unfamiliar with this term, you will be provided with the proper materials and references to know more about them. Right now, just understand that there is a module which is going to help you analyze the vibrations present in a model and look at the stresses that are developed on a long period. Finally, we have the drop test. So as the name suggests, if you want to look at the stress strain on a model when it's dropped, we go for this module. Here the solver uses explicit time integration to plot the stress and the strain contours at the time of impact. Here we initialize the simulation by providing an initial velocity and adding the gravity to the physics that is included in the solver. So I hope that this lecture gave you a brief idea about what FEA is about and how SolidWorks has different modules to help us perform various analysis on our model. So thank you guys for watching. I'll see you guys in the next video. Bye. Hey everyone, welcome to yet another video in FEA using SolidWorks. So in this video, we'll discuss about what a static analysis is and how it's different from a dynamic analysis and what are the other different types of analysis that is available in SolidWorks and when do we use them. Let's begin with the PPT. So structural analysis. So the term structure not only refers to the civil structures like bridges and buildings, but it also can be used to refer the mechanical parts that we often use in an industry. To understand the stress and strain produced by the loading on these mechanical structures, we perform finite element analysis to understand the behavior. Here in a finite element analysis, the unknown displacements are initially found out and then they are resubstituted back to get the reaction force and other derived quantities like stress and strain. Basically, a structural analysis problem can be classified into static analysis and dynamic analysis depending upon the loads that are acted upon. Apart from this classification, we do have 1D, 2D, 3D finite element analysis that is classified based upon the element that is used. We have several other specific analysis like the buckling analysis, fatigue analysis, which serve the purpose that they were designed for. So SolidWorks has separate modules for each of the special analysis. Now let's look at the basic classification of analysis, that is static and dynamic analysis. If you consider a static analysis, we assume the forces that act upon the model are quasi-static. In other words, the loads that are acted upon on the model increase gradually such a way that the acceleration, velocity, they can be neglected. While on the other hand, the dynamic analysis, all the inertial and damping effects are considered and we solve for the acceleration and velocity of the components before we find out the stress and strain. So compared to a static analysis, a dynamic analysis is much more time consuming. So also if you consider in a static analysis, you start the simulation at point A and if B is your final end, the intermediate results that you get may follow any path and get to the final results. Hence, you can never rely upon the intermediate values in a static analysis. On the other hand, in a dynamic analysis, if you have two destinations, the path will be precise that the intermediate values that you get for stress and strain are reliable and can be used. To be even more specific, let's consider bending of a cantilever beam and I fix it in this side. I'm going to bend this by applying a force. If we perform a static analysis, as the stress value increases throughout the simulation, we get a final stress contour. This final stress contour can be relied upon, while the intermediate results produced by the pseudo time stepping of the solver cannot be relied upon. This is not the case with the dynamic analysis. Here, if you apply the same load on the cantilever beam and perform a dynamic analysis, you can see how gradually the stress increases, and at each time step, at 1 second, 2 seconds, that is, if you want to look at the stress result at the end of 5 seconds, the results prior to the final step, that is the first second result, will be reliable as well. Hence, the dynamic analysis requires more computational effort than a static analysis. So, depending upon our requirement, we tend to choose either we want to perform a static analysis or a dynamic analysis. And finally, to put it short, if someone is interested in looking at the deformation at the end of loading, so they can just perform a static analysis, look at the final deformation. If you are interested in looking at how the deformation progresses, you can perform a dynamic analysis on it. Now let's get back to the slides. As discussed earlier, any material will have an elastic region beyond which it is going to behave non-linearly and finally end up in the failure zone. Hence, to capture all these non-linearities, we do have specific types of analysis that is classified as linear and non-linear. In order to capture the non-linearities in a static or a dynamic analysis, we have specific analysis types to differentiate between these loads. So, to understand it in a better way, let's open SolidWorks. Click on File, open a new part. Make sure the unit systems are as per your requirement. Now, click on the front plane, right click and edit sketch. Draw a rectangle using the corner to corner method. Use the smart dimension to input 50 mm and a 50 mm for both the length and the breadth. Click OK. Now select this circle, place it exactly in the center point of both the sides. Dimension it as 10 mm and click OK. Now in order to constrain this circle into the center of the circle, click on this dimension, select this side and choose this point here and input a value of 25 mm. Similarly, choose this side and select the center, input a value of 25 mm. Now that we have fully constrained this geometry, click on the features here and select the extrude option. Input a value of 5 mm and click OK. So now we are going to perform a static analysis on this part and understand when we need to perform a nonlinear analysis on such a simulation. So this finite element analysis on a plate with a hole is a basic problem that any FEA engineer would start with while learning a software. So let's proceed with the simulation. Click on simulation, choose a new study. Let's perform a static and click OK. Now for the material, let's select alloy steel, which is the default material. So the yield strength is about 620 megapascal. Click apply and close. Now that we have defined the materials properly, right click on the fixtures, select the fixed geometry and choose this face. Make sure you choose the face and not the edge here. Click OK. Let's apply a load on the other face. Select the face. You can see if you apply the load now, it's going to be a compressive type of force. We are interested in applying a tension force. So input a value of 1000 Newton and reverse the direction. Click OK. So let's use the default mesh for the demo purpose. So click on OK. So this is our meshed model. This looks fine. Let's proceed with the simulation and run it. Okay, now that our simulation is done, let's look at the results here. You can see the yield strength is about 6.2 into e power 8 and the stress values are well below this yield strength value. So this stress result is acceptable since there is a linear relation between the stress and the strain within the elastic limit. If you increase the force by a factor of 10, your maximum 1 measure stress should also increase by a factor of 10. So right click and run the simulation. So as you noticed that there was a similar change. So now let me increase the force value by a factor of 10 and rerun the simulation. So you can see in the legend, so we have a arrow pointing to the yield strength value. Thus, any value that is being plotted above this yield strength value is unacceptable. That is, we have to perform a nonlinear analysis to get realistic values from this simulation. Hence, in any case, if you are performing a static analysis and your stress values are above the yield strength value, you should not use those values. You need to switch over to a nonlinear analysis to get reliable results. Let's copy the same simulation and perform a nonlinear static analysis. Click OK and run this analysis. You can notice that the solver is taking much longer time than it took to solve a static analysis. And here you can see the strain values are not as high as the static analysis. That's because if you consider the stress strain graph, if the relation between the stress and strain is linear, you can see the displacement gets larger as the stress value increases, and when it enters a nonlinear region, as the displacement increases, the stress value doesn't increase that much. Hence, in the static analysis, our solver followed this extrapolated path such that for any value of load that we give, it received the corresponding stress and strain by just extrapolating this curve. Now let's move back to the slides. So depending upon the material stress contours, we should decide whether we need to move on to a nonlinear module or linear module to perform an analysis. Similarly, in the dynamic, we do have a linear dynamic analysis under which all the vibration and frequency analysis and finally we have a nonlinear dynamic analysis too. So as I mentioned before, static analysis involves time independent forces. Here the intermediate results are not reliable upon. In the linear static analysis, as we saw in the example, the relation is going to be a linear one. Hence, in order to capture the nonlinear effects, you need to use a nonlinear module. In the static module, all the nonlinear effects in the material are captured and the solver takes longer time to converge to the solution. So dynamic analysis is performed to understand the behavior of a material under time varying loads. So what is nonlinear analysis and why do we perform it? As we saw in the previous example, where the plate was pulled by a tension force, within the elastic limit, the stiffness of the module is assumed to be constant. So once the material crosses the yield strength value, its stiffness changes constantly with time. To capture all the nonlinear effects, the solver goes back to the material and evaluates the stiffness before proceeding to the next step. To capture the nonlinear effects, we need to perform a nonlinear analysis. This is the graph. So a linear static analysis will follow a path by extrapolating the elastic region. But a nonlinear analysis, after passing through the elastic point, the linear relation between the stress and the strain doesn't hold good anymore. So now let's look at some of the nonlinearities that can occur in a material. So nonlinearities can occur due to change in geometry. So when an object is acted upon by a force and we are performing a static analysis, solver detects large deformation, we will be prompted to perform a nonlinear analysis in order to capture the nonlinearities that were caused due to the change in geometry. So let's open SolidWorks and look at one such example. Click on the file and new part. Let's click the front plane, right click, sketch. Select the rectangle, draw a rectangle, smart dimension it as 50 mm, and 50 mm. Make sure you have the correct unit system. Here I have changed it. So go back to the edit sketch option, click on here, select 50 mm, select this and import 50 mm. So once you do that, go to features. So extrude the sketch to a distance of 1000 mm and click OK. Move on to the simulation, perform a new study, select the static model here. So now right click and apply the default material, right click on the fixtures, select fixed geometry, fix one end and click OK. And then again right click on the force, select this particular face and choose the direction in which you want to act this force upon. Make sure your force points downwards. Input a value of 500 newtons and click OK. Now right click on the mesh and choose mesh and run. So you can see we have got the result instantaneously. Now let's see what happens if I increase the force by a factor of 100. So here the solver has detected large displacement and hence is prompting you to switch over to a nonlinear analysis to get reliable results. In case if you want to switch over, you can just give an S. So apart from geometric linearities, we do have material nonlinearities. So material nonlinearities can occur due to two reasons. The first one being creep, another one is the elastic limit. In creep, if the material is acted upon by a load for a prolonged period of time, its stiffness doesn't remain constant. Instead, it starts varying with time. Hence, we need to perform a nonlinear analysis on such cases. Now, secondly, beyond elastic limit, any metal will move into the nonlinear region, while the nonmetals can behave nonlinearly within the elastic limit. And finally, apart from geometric and material nonlinearities, we do have contact nonlinearities, which are caused by the changing status of the contacts throughout the simulation. For example, if we have a simulation where we have a cantilever beam, there is a box which lies below the cantilever beam. Now if I apply a force on this cantilever beam, the stress contours on the beam will be linear until it makes a contact with the box below it. So once it makes the contact with this box, the stress contour on the beam will no more be linear even though it's within the elastic limit. Hence, depending upon the contact status, nonlinearities can step in even though you are well within the elastic limit. Now in SolidWorks, if you are performing a nonlinear analysis, you are provided with two options. First one being the static analysis, that is, you perform a nonlinear static analysis. The second one is a nonlinear dynamic analysis. Further, you have a small option called the use 2D simplification, wherein if your model is symmetric about a plane or an axis, you can use this 2D simplification option to run a 2D simulation and then view at the 3D results, look at the 3D plot by replicating the results along the axis of symmetry. So now let's look at how to use this 2D option and perform a nonlinear static as well as a dynamic simulation. So open SolidWorks, click on the file, choose a new part, and open the model that you have been provided with. So once you import the model, rotate, zoom and pan the geometry for any errors in the model. In our case, the model is fine. So let's proceed with the simulation. So before we proceed with the simulation, I'll explain about the simulation before we look into how to set up it. In this simulation, a punch is used to deform the sheet metal into the shape of the die. So now let's proceed with the simulation. During this process, we'll be looking at the stress that will be developed upon the sheet when it is being acted upon by the punch. Hence, to capture the variation of the stress during this process, we need to perform a nonlinear dynamic simulation to get accurate results. So click on the new study, select nonlinear dynamic 2D simplification and click OK. Here you need to select the plane about which your model is symmetric. In our case, it's the front plane, and we are going to have a depth of 0.015, that is the thickness up to which you need to replicate this 2D results to get the 3D object. Once you do this, you can see we have got the 2D representation of our model. Now click on the parts here and right click, apply the default alloy steel material to all the parts. Click on the sheet metal and apply plain carbon steel as the material. Now right click on the fixtures, click on fixed geometry, select the 3 edges of the die to fix the die in a position all throughout the simulation. Now right click and use the fixed geometry, select these 2 edges of the plate to ensure that the plate doesn't slip off during the bending process. Again right click on the fixtures, choose fixed geometry and expand the advanced selection. Select this portion of the punch and activate the translation along these 2 directions. Since the punch needs to move down to a distance of 10 mm, reverse the direction and click OK. Here now we have fixed the geometry and the punch will be moving down by a distance of 10 mm. Before you hit OK in the translation, we need to look at one crucial option that is available in a dynamic simulation. Here you have a curve that represents the loading in this problem. As you can see, in the x-axis we have the time and in y-axis we have the load. In our case, it's a translation load. So from 0 to 1 second, we are loading this geometry. At 1 second, we are applying the whole load. For example, let's say I have 5 newtons of load that needs to be acted upon. In that case, at 0 seconds, we will have 0 newtons. At the end of 0.5 seconds, we will have 2.5 newtons. And at the end of 1 second, we will have 5 newtons totally acted upon on the material. So we are increasing the load gradually but linearly in this case. And since the translation is along the negative y-axis, we have the graph pointing downwards. Now let's look at the various other options that are available defining load steps. So when you click on edit, you will be given option to edit your loading steps. In the first column, you have the seconds, and in the y, you have the loading ratio. In this current scenario, at 0 seconds, we have 0 loading ratio, and at 1 second, we have 1 as the loading ratio. Let's suppose we want to look at unloading type. Here, the maximum value of force will be applied at time equal to 0, and it will be gradually unloaded from the material. Finally, we have a loading and unloading type of graph. Let's look at it. You can see, so before 1 second, the load is applied and unloaded as well. In between the simulation, we reach the maximum load and gradually it is unloaded off. Just directly apply the load here. Click OK and hit OK here. And before we run the analysis, let's look at the properties. You can see we have been provided various options to adjust the time step and help in convergence of the solution. In our case, we are not going to change them. But if you face any convergence issue in your own simulation, just try to change them. Now, if you want to understand this time stepping in detail, let me demonstrate it using a small calculation here. I have at time equal to 0 and at time equal to 5 seconds. I am applying a force. At 0 seconds, it's 0 newtons, and at 5 seconds, it's going to be 10 newtons. Here, the solver will initially proceed by defining the stiffness matrix and start solving for the unknowns. But after it solved for the first step, while going for the second step, we define a time. We define a time step. In this case, let's assume it to be 0.1 seconds. Then the solver will move to 0.1 seconds and redefine all the matrix depending upon the previous step, find for the unknowns in this current step. After this particular step, it will again increment the solver time by 0.1 seconds, and this process will go on. In case, if your solver experiences convergence issue, that is, if the solver is not able to get the same result while iterating to find the unknowns, it will increase the time step by some factor. Here we have given the initial time step to be 0.1 and it may increase the time step to 0.5 seconds. Hence, after solving for the 0.1 second, it will move to 0.6 seconds. And this process continues until you have solved for all the 5 seconds. Hence, for this reason, you specify a minimum time step, help the solver converge to a solution. Now, let's go back to SolidWorks. Apart from controlling the start and end time, you have several other options that you can use depending upon your requirement. Let's click OK. Here, since we have lots of parts, we need to define proper contacts in order to avoid interpenetration of the parts. To understand what it is exactly, I'm going to run this analysis without defining the contacts properly. So as you can see, since we did not define the contacts properly, the parts have interpenetrated themselves. This is totally unrealistic because in real life, if a material needs to penetrate another material, it needs to follow a particular mechanism to fail the other material and go through it. So this is totally unrealistic. Hence, to avoid this, first hide the stress plot by right click on the stress, choosing the hide option. Right click on the component contact and select contact set. Since this die will come in contact with this sheet here, select the edges of the die. Make sure you select only the edges and not the face and define them as the source. Now for the target, select this edge of the sheet metal. Define a frictional contact and make sure you have no penetration selected here and click OK. Similarly, right click on the component contacts again and define another contact between this sheet metal edge and the edges of the die. Define the friction and make sure you have no penetration and click OK. In case if you are going to interchange the target and the source, you will end up getting a convergence issue and your simulation will fail. Now that we have defined the contacts properly, let's rerun the simulation and look at the results. Our simulation has successfully completed. Now right click on the stress and animate to look at the results. Now if you want to look at the 3D plot of this simulation, right click on the result and show as 3D plot. This 3D plot is created by replicating the 2D result along the depth distance that we defined earlier in the simulation. Right click on the result and click animate. And this is how we perform a 2D simplification nonlinear dynamic analysis on a 3D model. This way we will be able to reduce the computational effort and get accurate results. Now let's go back to the presentation. Before I proceed on with the presentation, let me show you another example where our model is symmetric about an axis. Let me import the model. Here you can see the 3D model is already simplified as 1/4 the whole model. Now we are going to simplify it further by selecting the axis of symmetry here. Let's begin by clicking on the simulation. Click on new study. Select nonlinear dynamic. Use 2D simplification and click OK. Here, since our model is symmetric about an axis, select the axis symmetric option. Choose the plane for cross section and then select the axis of symmetry. Once you do that, you will be provided with the 2D simplified model and you can proceed with the simulation. So I am not going to do the simulation for you. This will be provided to you as a challenge, but I will explain the problem statement here. We will be looking at the deformation that will be caused by the sphere when it is pressed onto the plate. So here this sphere will be moved forward and the plate should be fixed as it is. We will be performing a loading and unloading type of simulation and then look at the stress that is developed during this process. Now in case if you want to modify your contact distance or move your parts apart before proceeding with the simulation, click on the model here, choose the move body options and select the body that you need to move. Choose the translate option here. Then in our case we need to lift the sphere up by some distance. Let's say it's 0.5 mm. You can see we have lifted the sphere by 0.5 mm, the y direction. Now let's select OK. So here we have successfully lifted the sphere. Now we can proceed with the simulation. Let's move back to the presentation. Now with those examples, we have understood how to perform a non-linear dynamic simulation on a 2D simplified model. In SolidWorks, you have been provided with various models for the materials to perform a non-linear analysis. That is, if you have noticed properly in the simulation, as the punch presses into the sheet metal deforms like an elastic material. In other words, if you end up removing the die, the sheet metal will return back to its original position without any plastic deformation that has been occurred. This would look like unreal. It's because we have chosen the wrong material model to represent the behavior of the sheet metal. To define your material model correctly, right click on the edit material and in the model type, you have been provided with a list of options depending upon your requirement. So with the right settings, we can capture the plastic deformation that has been caused by the punch during this operation. So as I mentioned before, in linear elastic isotropic, the material properties are assumed to be constant throughout the x, y and the z direction, and after loading, if the material is unloaded, it will return back to its original position without any plastic deformation. In the linear elastic orthotropic, you need to define the material properties along x and y direction in order to perform the simulation. This way, you will be able to capture the behavior of orthotropic material, but this particular model will revert back to its original shape after the loads are unloaded. While choosing this linear elastic orthotropic, you need to input values for elastic modulus along y and z as well as Poisson ratio in all the other planes. To do this, you need to right click on the library material, copy it, paste it in the custom materials, and then input all these values before you use it in the SolidWorks model. Now, nonlinear elastic. Here this model is used to capture the effects of nonlinearities, but the deformations are still elastic in this model. In plasticity 1 measures, when the stress value are above the yield value, the plastic deformation sets in. So these effects will be captured accurately by this model. Apart from the plasticity 1 measures, we do have plasticity Tresca and plasticity Trucker pager, which are complex models developed over the plasticity 1 measures. Now, if we use materials such as rubber, which have high deformation rate for a small load, that is, even if they are in the linear elastic region, their displacement is large for a given load. To simulate all these effects, we use hyperelastic, and the viscoelastic model is used to simulate the different effects that is produced by the same material at different loading rates. Finally, using this nitinol model, we can model the nonlinear effects without allowing plastic deformation to set in, even though the model experiences high deformation. So by choosing the appropriate model, one can capture the deformation process of a material using SolidWorks simulation. I hope this lecture was helpful enough to understand the difference between using a static and a dynamic analysis in SolidWorks. Go ahead, use the models that you have been provided with and attempt the challenge that you have been given. I'll see you guys in the next video. Bye. Hey everyone, welcome to a new video. So in this video, we'll be learning how to perform a finite element analysis on a uniformly loaded cantilever beam using SolidWorks. So to begin with, let's open SolidWorks, click on the part modeling and click on the sketch module here. Select the sketch, choose the front plane and draw a rectangle. Dimension it as 0.03 and 0.03 on either sides, that is, it's a square. Now click on the features here, extrude the sketch to a distance of 0.5 meter, click OK. So this is the beam that we are going to use for our simulation. Now that we have drawn the part, click on the simulation and select new study. So we are going to perform static structural analysis on this beam. Select the static analysis and click OK. Right click on the part, click apply material and select the alloy steel, click apply. Now close the window. So first we are going to perform a 3D analysis on this beam. So let's go ahead, define the fixtures. Since this is a cantilever beam, let's fix one side of the beam and click OK. Now to apply a uniform load on this face, right click on the external loads, select force, select the face you want to apply it on and input a value of 1000 newtons, click OK. Now that we have defined the boundary conditions and the loads, right click on the mesh and click create mesh. Here you can use either the default option to slide over between the coarse and the fine mesh, or else you can click on this mesh parameters and manually import a value for the mesh that you need. In our case, let's use a 6 mm mesh, click OK. You can see the model has been meshed and the mesh is looking fine. So let's go ahead, run the simulation. You can hit this run this study option or click on this mesh and select mesh and run. So this is a pretty simple and straightforward simulation, hence it took very less time. So you can see we have the stress plot, the displacement and the strain plot for the beam. So we are looking at 1 measure stress here. So the maximum value of 1 measure stress is 5.8 e power 7 Newton per meter square. And if you look at the displacement, so right click on this, click on animate to view the animation of the simulation. You can even save this as a AVI file, but we are not interested in doing that now. Right click, and if you want to look all the plots in the same window, right click on the results, click compare results and click OK. So here you have the model along with the loads and constraints. we have the 1 mile stress in this window, and we have the displacement here, and the strain is being plotted in this window. We have successfully completed a 3D finite element analysis over a cantilever beam. Now let's consider this same part as a 1D model and look at the results. So to do that, click on the model and hit the simulation button, hit new study, rename the simulation setup as 1D static. Now since it's a 1D analysis, we are going to consider this whole geometry as a single beam element instead of discretizing it into small elements. So to do that, right click on the part. So first apply the required material. So right click on the solid part again and select treat as beam. So in our case, since the length to width ratio is very large, our part was directly considered as a beam. But if your length is not proportionately long with your width, you may get a warning saying the slenderness ratio is not large enough to treat it as a beam. Now that we are good to go, let's go ahead and define the boundary condition and loads for this 1D FEA. Right click on fixtures, select fixed geometry, select this joint and click OK. Now to define the force, right click, select the force, select the whole beam, and for the application direction, select the face. It's going to be a downward force of 1000 Newton. Click OK. Now right click on the mesh, create mesh. So after meshing the geometry, the 1D representation of our 3D model is shown in the screen. Now let's go ahead and run the simulation, and there you go, you have got the results instantaneously. Similarly, we can go edit the chart options and change it to floating, go to definitions, change the units to Newton per meter square, millimeter square, sorry, and now the results look meaningful. For the displacements, let's go ahead, change the settings, and the chart options should be floating, and OK. Yes. So apart from the standard stress and displacement results, since we have considered this whole part as a beam, we can request for beam bending moment and shear stress diagram for this particular beam. First, let's look at the shear force diagram. We have successfully completed the 1D FEA analysis too. Now finally, if you want to analyze the same beam as a 2D shell element, we can do so by clicking on the model, choose a new study, select static and rename it as 2D static. Now since it's a 2D element, we are going to consider this whole beam as a shell element. Before you do that, apply the material and right click on the part model, define shell by selected face. So we are going to consider this whole beam as one shell element with a thickness of 30 mm. Yes, and click OK. So now to define the fixtures, right click and select fixed geometry. And since we have converted this whole solid part into a shell element using this face, we need to define all our loads and constraints to this particular shell. Click on this edge and select OK, and right click on the loads, click on the force. Now to apply the force, select the face on which this is going to act, and let's select the direction. So it's going to act in the downward direction with the force of 1000 Newton. Click OK. Now right click on the mesh, create mesh. Here you will be provided options to vary the mesh parameters. Since it's a shell element, we can use 6 mm mesh. So this is the 2D representation of our solid part, which will be used for the analysis. Now let's go ahead and run the simulation. So we have received the results from the simulation. So let's go ahead and define the legends properly. Click on settings, and chart options, floating definition should be Newton per millimeter square. Yes. Now for the displacement, it's again going to be settings, chart definition, floating. Right click and show, and then right click on settings, chart options, floating. Yes, so we have successfully completed a 1D, 2D and a 3D FEA analysis for a uniformly loaded cantilever beam. So to view the results of all the three types of analysis, click on this result options and compare results, all studies in this configuration. Let me look at the displacement results alone for all three, 1D, 2D and yes. So let's select OK. Yes, and yes, so this is the model that we use for our analysis, and we have the 3D simulation results here, the 1D results and the 2D results. If you look at the values, we seem to have received approximately the same values in all three simulations. So depending upon your requirements, you may choose whether you want to perform a 3D analysis or a 2D analysis for a particular part. For example, if you have a part in which you have lengthy members and you are only concerned about the bending stresses in that lengthy members, then you can very well consider the member as a 2D element or a 1D element to avoid computational complications. So instead of going for a 3D model wherein you have a lot of elements, you can consider it as a 2D shell element or even a 1D element and look at the displacements and the stresses developed. Okay, that being said, let's first save our simulation setup. File, save. So let me save it in the PC using a new program. New folder, SolidWorks Simulation. So we have successfully saved the simulation, and now let's learn how to perform a parametric study using SolidWorks simulation. So to do that, so right click on any simulation. So in this case, I'm going to perform a parametric 3D analysis. So I'm going to select 3D static and then create a new design study. Once you do that, a complete new window will open up with your model and dialog box with various options like variables, constants and goals. If you just uncheck the optimization, you won't be able to access the goals, but I'll teach you how to use this optimization option. So what's the use of this parametric design study in SolidWorks? So why do we need it? Let's consider a case in which I want to increase the length of this member and change the material, or even try to change the width of this material. I need to go back to the modeling again, remodel my part and check if the stresses are below the required value. So instead of doing all this all over again, so in SolidWorks you can, in the variables, you can select the parameters that you need to vary and even input the ranges between which the values change, and in the constraints you can add a limit. For example, I can conduct several simulations and look at results which have a maximum factor of safety value as 2. And finally, in the goals, you can choose to minimize or maximize certain values. All this will make sense once we perform an example study. So let's go ahead and choose the parameters that we want to vary. So once you click the variables and add parameter, a dialog box is going to open up. So here, let's rename it as length. And for this length, it's going to be from the model dimensions. I'm going to choose the length here. So that is one parameter that I want to vary. The other one is going to be the width. And I'm going to choose this, yes. And next, apart from varying the length of the part, you might as well play with the mesh size. So to do that, click on this drop down menu. We're going to get this value from the simulation. go to the analysis, select the mesh, and once you do that, there will be several parameters that will be listed, and from that you can choose which one you want to vary. I'm going to vary the global size, and I'm going to initially start with a 6 mm mesh. Make sure the units are right, or else your simulation may end up with errors. Now you can even control the force value as a parameter. So click on the simulation, select the force, and I'm going to use 1000 newtons initially. That's it. Click OK. Now you can see all the variables have been added to this list. I'm going to vary the length, the force that is applied, mesh size, width, and for a better view, click on the table view here. Before you do that, make sure all the ranges make sense. My minimum length is going to be 0.5 and my maximum length is going to be 1 meter. Maybe, yeah, I'll go for 2 meter. The force ranges from 1000 newtons to 10,000, and the step is going to be 2000. For this, I'm going to step by 0.5 meter. My minimum mesh size is going to be, I'm going to use a 4 mm minimum mesh size and a maximum of 6 mm. The step is going to be 2 mm. For the width, the minimum width is going to be 0.03 and the maximum is going to be 0.09. The step is going to be 0.03. So here you would have noticed that I'm going to vary the mesh size, and this is what we call as a grid dependency test in FEA. That is, so you will be asked to perform the same simulation for different mesh values and look at the variation results. So once you perform several simulations for different values of the mesh, you will notice that after a certain refinement, the value of the output results will not change. So that's the value that you can rely upon from a FEA analysis. So SolidWorks parametric design study is very useful while performing such grid dependency tests. Yeah, now that we have populated this table, and let's define the constraints. Click on add sensor. I'm going to say that the factor of safety shouldn't be less than, yeah, it should be greater than 3. So that's my constraint, and I'm going to add another constraint saying that from the simulation data my stress values shouldn't go above 6G. Yes, so it should be less than 6G, and the minimum factor of safety should be greater than 3. Since the optimization check is on, I'm allowed to add a goal. So my ultimate aim is arrive at an optimum value for designing this beam with the minimum mass. So let me select this mass, and I'm going to minimize the mass. Okay, so I hope we have defined all the variables properly, and you can see that total active scenarios are 144. What do you mean by 144 is we have 144 simulations to run, and after running all this simulation, SolidWorks is going to pick the best value for you. It's going to pick the best or the optimum value for you and show it to you. So to run this parametric design study, click on the run button here. Wait for the solver to finish all 146 design scenarios. This is going to take considerably long time, and you can see how much time we have saved using this parametric design study. Imagine what would have happened if you are going to manually set up the simulation for each cases and look at the variations. So this is a great tool to use while you are performing parametric study. Okay, SolidWorks has completed 3 scenarios, and all 3 have failed our requirements. You can see in the GUI the model is being continuously changed as per the values we have given, as per the range of values we have given. So let's wait until all the simulations are done and look at the results. So as you can see, our target stress was 60 Newton per millimeter square, but seems like the value was not imported properly. I'm going to go back to the variable view, change this to 60 Newton per millimeter square. And click run. So let's wait again. So the stress is going to be less than 100. It's rough. So make sure the rest are same. So since we have more than 100 skill scenarios, I'm going to reduce the range between these values change. So let's say this is 0.5 to 1.5, and I have a step of 1 meter. So 1000 to 5000, step of, let's say, yeah, so 1000 to 6000, and step of 222, so 3, 5 and 7. Yes. So let's say we have a step of 2000, and for the mesh it's going to be, yes, for the width I'm going to have maximum of 0.06, step is going to be 0.3, and you can see now we have considerably reduced the number of design scenarios. So let's run the simulation again. This time it is definitely going to take less time, and we can look at the output results. Okay. So this concludes the video. Thanks for watching. You will be given a challenge to attempt on. I'll see you guys in the next video. Bye. Hey everyone, welcome to a new video in FEA using SolidWorks. So in this video, we'll be learning how to set up a buckling analysis for a Cyclonic separator stand using SolidWorks. To begin with, let's open SolidWorks and import the model for the simulation. So this is the model that we are going to use for the simulation, but since we are going to perform a buckling analysis for the stand alone, we don't need this Cyclonic separator, hence we will be suppressing it for the analysis. So let's begin. So now click on new study, choose buckling analysis from the list of analysis and rename it as no stiffener. And click OK. So from the list of parts, select the Cyclonic separator parts and right click, exclude from analysis. So this way we have suppressed the Cyclonic separator from the analysis. And finally we have the stand alone. So right click and insert a material. Let's use the default material alloy steel. And for the fixtures, since this stand will be fixed with the ground, we're going to define it by right click, insert fixed geometry, select the faces of the stand, and click OK. Now that we have fixed the geometry, let's go ahead and define a load for it. So we're going to apply a load on this face with the value of 150 kilonewton and click OK. Now let's mesh the geometry using a fine mesh. Here the mesh seems fine, so let's go ahead and run the simulation. the simulation is completed. We have a resultant amplitude plot here. So right click and animate. You can see how the part is going to fail. Now if you right click on the result and choose list buckling factor of safety, you can see that the buckling factor of safety is almost 10. That means the total force required to fail this part by buckling is 10 times the force that we have applied. So usually in a buckling load for any columns, the structure is considered to be safe if the buckling factor of safety is above 3. So in our case it's above 3, so our part doesn't fail this value of force. If I give 10 times more than this load, then our part may fail due to buckling. Now in case if you have a stiffener over here or even an additional stiffener over in the midsection, you will find that for the same load the buckling factor of safety increases. It's because the lengthy stands of the cyclone separator are strengthened by the stiffener. So you'll be given a challenge to work on and observe the changes as you add on the stiffness. Thank you guys for watching, and I'll see you guys in the next video. Bye. Hey guys, hope you're doing good. So in this video, I'll be giving you some assignment help to proceed with the buckling analysis challenge. I hope by this time you would have tried the buckling analysis on the cyclone separator stand and tried to attempt the challenge that you have been provided with. As part of the assignment, you have been asked to create a stiffener between the legs of the cyclone separator and do a design study to find the best position to place the stiffener. So now in this video, I'll be helping you model the stiffener in the step file provided to you. So let's look at the model here. So this is the model that you have been provided with, and in this model, we are going to attach a stiffener between the legs of the cyclone separator, and we are going to extrude it for some width. So here, as per the challenge, you need to vary the position of the stiffener, and you have been provided with the extrude width of this stiffener. So let's go ahead and open SolidWorks. Here, first open the step file provided to you, and once the model loads in SolidWorks, expand the model list and suppress the cyclone separator part. After doing so, click on File and save the model file as a SolidWorks part model with your convenient name. So hit the save button. Now that we have saved the model as a part file, open the part file that we saved just now. And open it. So once you open the file, since we are going to create a stiffener between the legs of the cyclone separator, we need to choose a plane to draw the sketch. So here we need to draw the sketch on this plane, and in our case the top plane aligns with the plane that we want to sketch the model. So right click on the top plane and hit the sketch option. Afterwards, then normal to option to view plane in a perpendicular direction. Here choose the rectangle drawing options and click on the corner to corner method to draw a rectangle. Make sure you select the point exactly so that your stiffener is in contact with your legs, else you may end up having a discontinuity between the stiffener and the legs and the cyclone separator legs. So we have now drawn the first square. Repeat the same for the inner square and click OK. Here we have created the sketch for the stiffener. Now click on the features and choose extrude. Since we are going to position the stiffener, choose the offset option. Let's say we are offsetting it for 1.5 meters. As you can see, it has gone outside the model. So reverse the direction. For time being, let me choose 1 meter, which is exactly in the center. Now for the width of the stiffener, I'm going to choose 10 mm. Make sure you make a note of the units that we are using. So here we are using meters. So while giving 10 mm, I need to specify it. So I'm going to give 75 mm as the width of the stiffener. Here we have successfully created the stiffener. Hit the OK button and now proceed with the buckling analysis. So to click on the simulation, select new study. From the list choose buckling Name it as per your convenience. Click OK. Now for the demo purpose, let's apply the default material and fix the geometry. Zoom in and make sure you are well aware of what you are selecting. In case if you select the wrong face or the edge, we may end up getting the wrong results. So pay attention while selecting the faces to constraint and hit OK. Now let's apply the loads. We are going to apply a load of 150 kN and hit OK. Now let's use the default mesh and run the simulation. So once the simulation is done, you can very well right click on the results. Look at the buckling factor of safety. It is 27, so it's pretty high, and I think we are good with the position of the stiffener, but it may even be higher than this value at any other position of the model. So let's find it out by performing a design study. Click on the new study, choose design study and select design study options. For the list of variables that you need to vary, choose the parameters that you think would affect your design. So here, as part of the challenge, you have been asked to vary the position of the stiffener. So select the dimension and rename it as offset distance and click OK. So we have successfully parameterized the position of the stiffener. So once we have added the parameter, so we need to define the range between which we want to vary the position of the stiffener. Let's say I want to vary it between 0.25 to 1.75 meters, and the change between two variations is 0.25 meter. So after doing it, we need to constrain the design study. So click on add sensor, choose simulation data, and in this case I'm going to limit the buckling factor of safety to a value greater than 25, and this comes from the simulation study that we have named as test 1. Now the ultimate goal of this design optimization is going to be to maximize buckling factor of safety. So here there may be many design studies that would have a value greater than 25, but out of all the simulations that yield a value that greater than 25, I need the maximum value. I need the combination which is going to yield the maximum buckling factor of safety. So let's go ahead and run this optimization. Here you can see in total we have 9 scenarios, and after completing the first scenario, a table will be displayed. So here it is. It has completed the initial study. You can see the position of the stiffener is much high, and I hope by the next iteration it should move down. Yes, so it is moving down. You can see the first simulation yielded a buckling factor of safety value of 12, which is much less than the constraint value 25. So it is colored as red. So the value of buckling factor of safety has increased from 12 to 15. So we have one scenario which has passed our constraint. Okay, now our design study is complete. You can see out of all the scenarios, when the stiffener is placed at an offset distance of 1 meter, it yielded the maximum buckling factor of safety value with a value of 27. So that is our optimum design value. So we have successfully completed a design study on the Cyclone separator stand. Since we used only one parameter in this case, we had only 7 scenarios. In case you are going to have more parameters to vary, you may end up with more number of iterations for the solver to check. So I hope this video will be helpful for you while attempting the second part of the challenge. Thank you guys for watching, and I'll see you guys in the next video. Bye. Hey everyone, welcome to a new video in FEA using SolidWorks. So in this video, we'll be learning how to set up a fatigue analysis for a S-hook using SolidWorks simulation module. So before we proceed with the simulation, we'll understand why we are actually doing this simulation. So as you would have seen in any day-to-day application, we have the S-hook in a gold ornament So we often bend the S hook that is present in this gold ornament to wear and remove it. So now, since we subject the member to repetitive loads, we are here to study the life and behavior of the part by performing a fatigue analysis on it. So to perform the analysis, I have created a model for the S hook, and let's open it up in a separate window. So here in this model, so in real life we fix this particular portion of the hook, bend the other section to enable the connecting member to slide into this part. So here this particular portion of the member is bent and rebent to accommodate the connecting member. So we are going to apply the same load here, that is, I'm going to fix this region by a constraint, by fixed geometry constraint, and after doing that I'm going to subject this particular portion of the member to a force of 50 newtons and apply a load and predict the life of this part when subjected to 1500 cycles. So let's go back to the presentation. Before we proceed with the fatigue analysis, so let us understand the use of SN curve in a fatigue analysis. So the SN curve for any material gives us the relation between the maximum stress that a material can withstand before failure after subjecting to a number of cycles. So here the stress is plotted in the y-axis and the number of cycles is plotted in the x-axis. So as I mentioned before, we are looking at a SN curve. You can see that the maximum stress value is plotted in the y direction and the number of cycles is plotted in the x direction. Here, let's say I have a material and I want to check the maximum stress that it can take after 100 cycles. So I just extend this point here. Note the corresponding value for the maximum stress that can be allowed. Before you proceed with the fatigue analysis, you need to perform a static analysis on the part so that you understand the type of stress that is developed in your part to predict about its fatigue life. So here, SolidWorks provides us with 4 types of loading. The first one is fully reversed, zero based, loading ratio, and then finally the fine cycle peaks. Fully reversed. So as the name suggests, the maximum and minimum load that is being applied upon the material has the same magnitude except for the variation in the direction. Thus, the loading ratio is taken as -1, and if you look at the graph, here you can see we have subjected the material to a maximum load of 1000 and we go for a value of 1000 newtons in the other direction. A very good example would be the gold chain that we are going to analyze in SolidWorks. Here if you apply a 50 newtons to open the S hook, you then apply a value of another 50 newtons to close the S hook. This way the magnitude of loading is the same while the direction is reversed. So that is what is meant by fully reversed. Now the zero based. Here after subjecting the material to a maximum value, you remove the load and then reapply the load again. So this way you have the maximum value as the load you applied and the minimum value as 0. Hence the loading ratio is taken as 0, and the graph here shows exactly what the scenario in zero based loading is. A good example for this would be a door knob, where you pull the knob with some force, let's say it's about 100 newtons. So and then close the door, thus removing the load on the door knob. Again you apply a force and this continues. So this is what zero based loading condition looks like. Now the other type of loading that you can give in SolidWorks is using loading ratio. Here you have a ratio between the maximum and the minimum load that is applied. So once you give the maximum load and input the loading ratio, the software automatically deducts the minimum value and then proceeds with the simulation. The graph may look something like this, where you can see the maximum value is something here and the minimum value is not exactly the same in the opposite direction, but it's just offsetted a little bit down. So there is a loading ratio of some value between -1 to +1. Finally, we have fine cycle peaks. Here SolidWorks provides an option to import the stress values from the various simulation that you have already carried out on the part using SolidWorks simulation module. So now let's look at the results that can be inferred from a fatigue analysis. The two types of results that one can request from a fatigue analysis would be damage and the life. First, the damage. From this particular result, we can understand the percentage damage done to the material by exposing the same to a given number of cycles. This value varies from 0 to 100 depending upon the damage caused. Next, we have the life. This life is defined in cycles, that is the number of cycles the part or the material can withstand before experiencing any failure. You will understand this in a better way when we proceed with the simulation. So let's proceed with the simulation. So to do that, import the model in SolidWorks and then zoom, pan and rotate the geometry to check if the model is perfect. So once you do that, click on the new study here, and before you proceed to perform a fatigue analysis, click on a static analysis. Since the variation of the stress can be studied only on a static analysis, using the result from the static analysis, we can proceed to perform a fatigue analysis. Now right click on the S hook and click on apply material. Choose other materials and select pure gold. Click apply. Once you do that, right click on the fixtures, click the fixed geometry, and as we have discussed previously, select these two faces and fix them. Now right click on the loads, create a force on this particular face for a value of 50 newtons and click OK. Let's use the default mesh and run the simulation. We can see we have obtained the results instantaneously. Just animate and look at the application of the loads. Now that we have completed the static analysis, let's proceed with the fatigue analysis. So click on new study and select fatigue. Here you will be asked whether you want a constant amplitude events with defined cycles or variable amplitude, harmonic fatigue, or random vibration. So we'll be doing only fatigue analysis due to constant amplitude. I click OK. Here right click on the fatigue and click on the properties. From the properties of the simulation, you can select the different settings depending upon your requirements. So you have been given different failure theories which can be chosen to obtain the results, and right now we are not going to change anything, so click cancel. Right click on the loading and click add event. Here, since we are going to apply a fully reversed kind of load, make sure you have a fully reversed option here selected here. I'm going to check if this part will sustain 1500 cycles for a given load and click OK. Once we do this, we are all set to proceed with the simulation, but we haven't yet defined the SN curve for this simulation. So right click apply or edit fatigue data. We have an option to derive from the material elastic modulus. Select that, and we have a table that is populated here. Click view to plot data in the SN curve. Here you have the number of cycles. This is the maximum stress that is allowed, and click apply. We are now good to run the simulation. Let's run the simulation here, and we have got the damage as well as the results in live. Before we could infer anything, right click on the legends, click chart options and change the scientific notation to floating. Click OK. Now for the results, right click show. Similarly, right click, do chart options and change it to floating. Click OK. So first let's have a look at the damage. Here you can see the portion that is colored by red. There has been maximum damage percentage of 200, while on the other side of the bending we have a maximum damage of 50%. Let's look at the life now. We wanted to check if this particular part will sustain for 1500 cycles, but since most of the portion which is colored red is going to fail within 746 cycles, this particular part will not sustain 1500 cycles without any failure. So we need to either change the material or improve the design by adding some more thickness to the part. So now we have successfully completed a fatigue analysis on this S hook. Try this simulation again and you will be provided a challenge to work on. Thank you guys for watching, and I'll see you guys in the next video. Bye. Hey everyone, welcome to a new video in FEA using SolidWorks. In this video, we'll be learning how to set up a drop test simulation using SolidWorks. So before we proceed with the simulation, let's understand the model that we are going to use for the simulation. Here we have got a PCB board on which we have placed several electronic parts. As you know, any electronic appliance consists of PCB boards over which all the electrical components will be soldered on. Hence, when this electrical appliances drop, we need to make sure that the soldering that holds the electrical components with the PCB doesn't fail immediately after dropping it. Hence, to validate such cases, we perform drop tests on the PCB board and understand the stresses that will be developed while dropping them. Let's proceed with the simulation. Click on a new study, select drop test and click OK. For demo purpose, I'll be defining the materials for the components as such, but in realistic simulation, you need to make sure that each component has the exact material using in your real life. So for the PCB board, let's apply the material, go into plastics and use PBT general purpose. For the rest of the items on the board, let us use alloy steel and click OK. Now for the setup of the drop test, we are going to drop it from a height of 1 meter, that is calculated from the lowest point to the point of impact. So for the gravity direction, let's expand this tree and then select the front plane and select the top plane here. Reverse this direction. Our target orientation should be normal to this plane of gravity. So now click OK. Once we do this, if you right click on the result options, you will have a solution time after impact. That is, once the part is dropped, it would experience stress propagation throughout its whole body through elastic waves until which the oscillations are present. Usually, once you set up the simulation, this solution time after impact is automatically chosen by SolidWorks. You can manually change it to. We are not going to touch it now. So right click and run the simulation. Since it's going to take a long time while running the simulation, I have already done this simulation. Let's have a look at the results. So here, this is the stress plot that we have received. Now if we animate, you can get a good idea about what has been going on. So you can see the part is dropped and the stress propagates all toward the body. Here at the edges, you can see there is high values of stress. We need to add some more solder materials. Make some design changes to make sure the components do not come off while such kind of an impact. Now we can look at the displacement plots, and this is how a drop test simulation is performed using SolidWorks. So thank you guys for watching. I'll see you guys in the next video. Bye. Hey everyone, welcome to a new video in FEA using SolidWorks. So in this video, we'll be learning how to set up a frequency analysis using SolidWorks simulation. So let's proceed with the lecture by looking at what a frequency analysis is and why do we do it, and then finally proceeding to perform a simulation to understand how we can do a frequency analysis using SolidWorks. So frequency analysis. So any material vibrates on its own natural frequency even when it's at rest. So before we use any part in an assembly, we tend to study the frequency at which it naturally vibrates to make sure that the operating range of the model doesn't fall near this frequency. This is to make sure that the amplitude of vibration of the model and the assembly doesn't multiply to produce a displacement much large enough to disturb the assembly. So this particular phenomenon is called a resonance, wherein the frequency of the motion of a part matches with its natural frequency. The amplitude multiplies, thus resulting in resonance. So it's very crucial to perform a frequency analysis on any part before using it in any mechanical system. A material vibrating at its natural frequency has a tendency to displace in any direction. This tendency is studied by looking at the mode shapes at the vibrating frequencies. The displacement produced at the natural frequency of the material are referred to as mode shapes, and this mode shape can vary from material to material. That is, if you have a material producing a mode shape and at the same frequency, the mode shape created by a different material will be different. Also, if a material produces a set of mode shapes at a specified frequency, for the same frequency, the same material will produce a different set of modes if the loading conditions are changed. This will make more sense if we just look at a simulation to understand this phenomenon. Let's open SolidWorks, click on this file and open a new part, choose a plane and right click sketch, draw a rectangle. Before you dimension it, make sure you are in the desired unit system. I have chosen millimeters. Now right click on the sketch again, edit sketch, dimension the same as 50 mm and 25 mm. So this way we have specified the cross section of the beam that we are going to analyze. Now click on the features select the extrude option here and input a value of 1000 mm, that is 1 meter. So this will be our beam. Click OK. Now let's proceed with the simulation. Create a new frequency study. Click OK. I'm going to use the default alloy steel material and first perform a 3D frequency analysis. So right click on the fixtures, create fixed geometry. Here I am going to apply a fixed constraint on either ends of the beam. Thus this is a fixed beam. Right click and create a mesh. I am going to use the default mesh. This looks pretty decent to proceed with. Now right click on the frequency, click on properties. Here we have several options to specify to the solver to proceed with the simulation. I'll talk in detail about each of the specification in the lecture. So let's click OK. Now right click on the frequency and hit run button. So our simulation is done here. Let us have a look at it. So this is our first mode shape. Let me animate it at a much faster speed. And similarly we have the second mode shape. You can see this is in the other direction. Previously our mode shape was vibrating in the Y direction and this one is vibrating in X direction. So see, the vibration is along the X direction, while for the first mode shape it was on the Y direction. If you look at the third mode here, we have a node in between these two mode shapes. So let's animate, and we have 1, 2 and 3 modes in this mode shape. Now similarly, if I have a look at the fourth mode shape, it's in the other direction. And finally the fifth one, we'll have an additional node. So we have 1, 2, 3 and a 4. Okay, this is a 3D frequency analysis that we have done currently. But let's look at the results if you are going to proceed using a 1D or a 2D analysis on this beam. So to do that, right click and copy the study. This is frequency 1D analysis. Click OK. And now since we'll be performing a 1D analysis, right click on the solid part and treat it as a beam. After we define this as a beam, all the constraints need to be redefined. So right click on the fixtures, click edit definition. Now clear all the previous selections, select these two joints here and click OK. Once you have defined the fixtures properly, go ahead and mesh the geometry. You won't be given any options to mesh the geometry because it's a 1D mesh. Now right click and run the simulation. We have arrived at the same result that we had from a 3D analysis. We can even have a look at the resonant frequencies by right click on the results and list resonant frequencies. So this is the first resonant frequency occurs at 133 Hz and the second is 267. It goes on. If you look at the 3D analysis and right click on the results, list the resonance frequency, it's almost the same results. So before we infer anything, let's proceed with the 2D analysis. Right click on the study, rename it as frequency 1 2D, click OK. Since we need to create a 2D part, right click on the geometry, first convert it into a 3D by clicking on treat as solid, which was previously there. Now that we have got the 3D geometry back, right click on the geometry and open the shell manager, select this face, input a thickness of 3 mm and click OK. So once we do that, right click on the fixtures again, edit definition and choose this edge as well as this edge to constrain the geometry. Now right click on the mesh, create mesh, we will use the default mesh right click on the frequency, run the analysis. Since we have defined the thickness of this part wrongly, let's go ahead and right click on the shell definitions here. Make sure you input a value of 25 mm for the thickness here. By defining this as 25 mm, we accurately represent the 3D model which was 25 mm thick using this shell here. Now right click, rerun the simulation. Then right click on this results, list the resonant frequencies. You can notice that we have arrived at the same set of resonant frequencies as we have received from the 1D and the 3D analysis. Right click on the second mode shapes and animate it. Similarly for the third, fourth and the fifth. Now that we have understood the different shapes that is produced by a material when constrained by a given boundary conditions, let's go ahead and duplicate the same study with the same material. I'm going to perform a 3D frequency analysis on the same material but with the different boundary conditions. This time I'm going to right click on the fixed constraint, remove one of the face that we have selected, that is I'm going to use fixed constraint on one side. My beam will behave as a cantilever beam right now, and run the simulation. You can see my first mode shape vibrates in such a direction and my second mode shape differs, and my third, this looks a little bit different than the both side fixed beam. So you notice that there were major changes in the mode shapes for the same material for different loading conditions. So let's proceed with the presentation. So SolidWorks provides you with two solvers to solve your frequency analysis. They are namely FFE Plus and a direct sparse solver. So as mentioned in the slide, so FFE Plus is going to use a iterative solving technique to solve for the unknowns, while the direct sparse solver uses a direct inversion technique to find the unknowns. Each method has its own pros and cons. In case you want to study more about how these solvers work, take a standard finite element analysis book and refer about solving a matrix iteratively and direct inversion. In case if you are not worried about how the solver solves for the unknowns, just consider it as a black box approach and proceed with your simulation. So since both the solvers use different techniques, the computational time that each solver will take will vary between them. SolidWorks has provided us with different options to set up our frequency analysis. The first one being specifying the number of frequency that we want to look at. That is, for a given material under a specified load condition, we can look at n number of mode shapes. But by specifying the number of frequency we want to look at, we restrict the solver to stop a given set of mode shapes. Secondly, we can specify the frequency range between which we want to look at the different mode shapes produced. Finally, using the upper bound frequency option, we can fix a upper limit beyond which the solver will not proceed further to find any mode shapes. We'll look at them, and this is how the options look like in a SolidWorks simulation environment. You navigate to this by right clicking on the frequency analysis and selecting the options there. Incompatible bonding options. So if your model is going to consist of several contacts between parts inside the model, the nodes may not be perfectly matched with each part in order for force to be transferred. So SolidWorks has a set of algorithms to tackle this problem. This problem can arise because the geometries are not even throughout, the mesh size is not consistent throughout. In order to tackle this problem, SolidWorks provided us with three options. The first one is the automatic, the second is the simplified, the final one will be the more accurate option. Automatic option is the default option chosen by SolidWorks simulation, wherein it considers both the surface as a whole to define any contact. But in case if this approach is found to be slower, the solver automatically chooses node to surface option to proceed with the simulation. Secondly, we have simplified option which uses node based contact definition. At last, we have the more accurate solution which is going to take a longer time but yields good results by using the surface to surface contact alone. The other options provided by the solver are, you can choose if you want to simulate the in-plane effects of a geometry. That is, if you consider a long beam, when you subject it to a compressive force, for the same load as the object deforms, the stiffness of the material is going to increase because there is a variation in the cross section. While if you are going to elongate the same part, Due to the thinning of the cross section, the material softens. So this is called the in-plane effects. In case if you want to switch this effect to be on or off, that is if you want your solver to check for the stiffness depending upon how the cross section of the model has changed, you can choose this option. Finally, we have the soft spring options. This comes into play when you don't have a proper boundary condition or constraint to fix the geometry in that environment. You can use this option only when SolidWorks prompts you to do so. Then we have the flow and the thermal effects. Apart from using an component in a vibrating environment, a building structure can be acted upon by a wind which has its own frequency of flowing over the building. And we can study the effects of this flow frequency on the building by adding it into the loads. Similarly, thermal effects can also be studied by specifying the temperature and frequency of heating or cooling up. So now let's proceed. So this is how the options for flow and thermal effects frequency analysis is going to look like. Now to the results that we get from a frequency analysis, we get to look at different mode shapes at different resonant frequencies. We can also have a list of resonant frequencies for a given part with the mass participation factors. That is the contribution of a particular part along with its mass in a particular mode shape. So this way you can increase or decrease the mass to reduce the effects of the vibration. Finally, we can plot the resonant frequencies against the mass. So now let's proceed to perform a frequency analysis on a printed circuit board using SolidWorks. Open SolidWorks. Click on the file options. Click here for new part. Click on the open and navigate to the part file provided to you. I'm going to use PCB circuit. You will be provided with this geometry to practice this exercise. Let's proceed with the simulation. Any printed circuit board has a set of components which is going to be soldered over to the board to perform a given set of operations. So when this particular printed circuit board along with its components is placed on a mechanical system, the vibration on the mechanical system do not fail the soldering connections of the electronic components in this printed circuit board. So we do a frequency analysis to study the vibration pattern of this printed circuit board, and using that information we'll make sure that the operating frequency of the mechanical system does not induce a failure in this printed circuit board. Further, the soldering strength is also enhanced after performing a frequency study in the printed circuit board. Let's proceed with the simulation. Click on a new study, choose the frequency system and rename it as per your convenience. Change it as test 1. Click OK. Now before you proceed any further, click on the part here. Right click on the part. This is our printed circuit board. So to apply the material, select apply material, navigate to the plastics, select PBT general purpose and click apply. So for these two microprocessors, I'm going to select the gold as the material. After doing that, select all other components and for time being, click apply edit material and apply the default alloy steel. Now that we have defined all the materials, let's go ahead and define the connections. So right click on the fixtures, click fix geometry. Since this board will be fixed onto a system by adding screws on this holes, let's select the surface and fix the geometry. Make sure you zoom in and select the desired entities. Zoom in further, select the face here, zoom out, zoom in, select this face here and click OK. Now that we have defined the fixtures and the materials, let's go ahead and mesh the geometry. Create mesh. I'm going to use a mesh parameter with the minimum size of 2 mm. Click OK. If you have a part in this geometry which is smaller than your minimum edge limit, your mesh will fail. So in my case, I have successfully created the mesh. I need not worry about refining it a little bit further. And let's go ahead and run the simulation. Okay, looks like our simulation is done and we have got 5 frequencies here. since we have not changed any settings here, which by default at 5 frequency. So let's look at them one by one. So this is how our first mode frequency is going to vibrate. Now the second one. Now right click on the results, look at the list of resonant frequencies. Here you can see our first resonant frequency is at 40 Hz, the second one is at 56 and the third one is at 116. So when you are going to use the same component in any system, you make sure that your system does not operate at any frequencies near this in order to avoid any damage to your electrical circuits or electronic components inside it. So now we have successfully completed a frequency analysis on a PCB board. You have been given a challenge related to frequency analysis. So go ahead, try that challenge. I'll see you guys in the next video. Bye.